Okay, this is problem 6-26. It's on page 346. I'll sketch it up here, and I have not worked this one out ahead of time, so please pull out your calculators because I will need some help here. Let's see, we've got a piece of channel, and I think I've told you guys this, but I'll remind you. These standard shapes, when you're given dimensions of them in the back of your book, just know if you actually order any of this and you make something out of this, they're not exactly that size. Sometimes they're oversized, sometimes they're undersized. And this bit me a little bit. I was designing a part, well actually designing a laminator, and I had a piece of C-channel on it that was about, I think it was about a foot wide and about 6 or 8 inches deep, I don't remember. And it was fairly thick. It was probably 4 feet long. So you can imagine this weighed a fair amount. You know, it's not something you can pick up by hand. Well, I looked up standard shapes and looked up the width of this thing, and I designed some other parts that fit around it. Okay, so I had a shape something like, well, basically something like this. So the dimension from here to here was really important because I had stuff already designed on either side, right? And so the channel had to fit in between it. Well, it came in, it was about probably an 1/8 inch oversize. I'm sure the machinists in the machine shop were not real happy with me when I said, hey, can you mill a little bit off the side faces of this thing for me? And they had to wrestle with this huge, heavy piece of C-channel. I'm just glad it wasn't some of the bigger pieces I included. Learned my lesson on that one. So sometimes they're oversized, sometimes they're undersized. You just have to know that when you're designing. So anyway, we've got 2 steel pieces. The top one is C12 by 25. The bottom one is the S shapes, which are I-beams, 12 by 50. Okay? So let's go back to the back of the book and see if we can find some properties for these, because what's going on here is we're welding these two together, and we'd like to find out how much area this has. Also, what is the area moment of inertia? So let's go back to the back of the book for the shapes and find these standard shapes and write down their properties. Let's see. These are S shapes. No, those are I-beams. Those are aluminum anyway. I need steel. W shapes and S shapes. Okay. Page 702 and 703 have the S shapes in standard units and in metric units. Now, looking at the designation, the S12 by 50, you think that's metric or English? It's metric. That's right. So let's see. S12 by 50. Wait a second. Oh, maybe it's not.
It's in English.
It is English. Yeah, that is English. Okay.
J.
Yep, J. Reference J. Okay. Why are they saying reference J?
So it's 12 by 50.
Well, anyway, this probably comes from some other reference. What we need is the area. So let's see, the area is 14.6 square inches. The depth is 12 inches, so that tells us the overall height of the I-beam. We're not particularly interested in that right now. I'll go ahead and write it down. We may need it later.
Could you do this in Excel also?
Pardon?
Could you do this in Excel?
You could do this in Excel, but it's not quite the same as what we had last time. Okay, I'm going to do this one by hand, and you can do it in Excel if you wish. How would you do it? Well, you'd have to type in the area. You'd have to type in the centroid. That part would be the same. Let me look at the spreadsheet and see what else there would be. AY, we calculate AY. Yeah, you could just type in the number, I guess, and it should calculate it fine. I may as well give it a shot, I guess. What we really want is the area moment of inertia. Now, look over on the right-hand side of the table. You'll see there's an axis XX and an axis YY. We're interested in the area moment of inertia, essentially about a horizontal axis. Now, like the area moment of inertia about the horizontal axis that's through the centroid of the combined area. Okay, so I'll have to find out where that axis is located, but then I'll also have to get the appropriate area moment of inertia. So do you see why I'm going to go for IXX? Okay, now understand, this will not give me the area moment of inertia of the I-beam about the centroid of the combined shape, but I can use the parallel axis theorem to move that axis to wherever the centroid is located. Okay? Am I confusing anybody? Clear? Have you done all this in other classes? No? Okay. All right. You guys are doing well then. I'm proud of you. All right, so J, we've got 303 inches to the 4th power. Okay, the other thing I want to find out is the location of the centroid. That would be up at 6 inches. So let's just jot that down while we're here. So Y sub, let's just use I for I-beam, is 6 inches from the bottom. Okay, I think that's all we need. If we need more, we can come back to the page. Now let's go for the C channel. And C channel I think is at the beginning. Yeah, here we go. C shapes. It is a 12 by 25. Let's see. There it is, 12 by 25. Look at page 698. Look at reference row D. Area for this shape is 7.35 square inches.
698.
Let's see, 7.35 square inches, I mean. And the area moment of inertia, do we want the area moment of inertia about the x-axis or the y-axis? It's going to be about the y-axis. Do you see why? Look at page 698 if you're not already. I'll show the video camera this for the same. Yeah, it's flipped, right? So the x-axis runs this way, y is this way. Our orientation is actually like this, okay? So that's why we were going to use the I-y-y properties. I won't write an x-x here, although you could say we have an x-y coordinate system in this orientation. I'll just write it down so it's not confusing. So I-y, well, I'll tell you what, let's just put y-y so you know where it came from. Anyway, row D is what we're looking at. Yeah, so 4.45 inches to the 4th is the area moment of inertia we need for that beam. Okay? Now, where is it located? Let's see, they show the centroid. Here we go. Let's see, X is the dimension I'm looking at. Notice it's measured from the top. And let's see, that is 0.674. Does everybody see that? So the distance from here, let me change colors. So the centroid of the C channel's about there somewhere. And the height here is what they're calling X. And they say it's equal to 0.674 inches. Okay? All right. Calculating the total area is trivial. That's straightforward. We'll just add the two areas together. All right? So let's do that first. So the total area would be 7.35 plus 14.46. I guess if I'm going to use a spreadsheet, I won't need calculator help. Let me turn this TV back so you guys can see it. And of course, if you're watching the video, you can just download the spreadsheet. I'll attach it as well. All right, we just finished working on problem 20. Let me save this as a new one so I don't accidentally overwrite the old one. Let's see, this is problem number 26. All right, we're going to get rid of, well, we'll just clear out, clear out 4 rows because we only have 2 shapes here. Clear out 2 moments of inertia. There we go. So 1, I guess I'll make the I-beam, and then 2 will be the C channel. So the total area, or the area for the I-beam is 14.6. And the location from the bottom is 6 inches. The area for the C channel is 7.35 square inches. And the distance, here we'll have to be a little more careful. Let's see. We need to know the thickness of that C channel. I forgot to get that while I was back in the reference area. Let's go get it. Anybody have that web thickness?
0.387.
D? Am I looking at the wrong page? Page 698, right?
Yeah.
Flange. Looks like the average thickness is 0.501.
Yeah, the average thickness.
Oh, web thickness. I'm looking at the wrong thing. Thanks. Yeah, so 0.387. Thank you, guys. You're right. So 0.387 is this thickness here. So from here to here is 0.387. Did I remember that correctly? Okay. Why do I need that? Well, that's the distance from here to here. Or, well, 12.387 is that total distance. I'll subtract off this x distance to find out how far the centroid is from the bottom. So in the spreadsheet, that's why I'm going to type equals quantity 12 plus 0.387 in quantity minus 0.674. Again, just let the Excel do the work for me. All right. Now I need the area moments of inertia, but I have those. So IXX for the I-beam is 303 inches. And for the C channel is 4.45. And what we're going to do now is use the parallel access theorem by hand to make sure that the spreadsheet's working the way we think it should, because what we've got, this IXX is the area moment of inertia for the I-beam about its centroid, the 6 inches up. But the final centroid of the combined shape is up a little higher because it's going to be weighted by this area. Okay, so we'd like to find out where that centroid is located and then calculate the area moment of inertia about it. How do we do that? Well, it's kind of like finding a moment balance. Here's the way I think about it. I think about it as two areas. These two areas are represented by weights, basically. This will be the centroid axis. You know what? Here, let's do it this way so it matches what we've got there. So this will be the area of the C channel, 7.35 square inches. This will represent the area of the I-beam, which is 14.6 square inches. Okay? And then the distance, I shouldn't write that way. Make sure I get this right, make sure I'm thinking right. The distance that this one has is going to be 6 inches. And, wait a second, let me think for a second. I'm getting confused. No, that's the moment. Oh, I know what I need to do. I'm getting confused because I'm used to drawing it the other way. Let me think for just a second. Okay. Well, the spreadsheet does it for us, but we're basically doing the same thing the spreadsheet does. Whoops. Here's my camera. Yeah, it's on the screen. Okay. I think of this as a moment, basically the moment of this area, but that's not going to. That's just going to be confusing. Let's go the way the book does and just do it the same way. So we want to find the centroid, right? So to find the centroid, all we have to do is multiply each of the areas times their distance to their own centroid, which is 6 inches. Okay, add to that the other area, 7.35 inches squared. And it's not just the distance, it's the distance squared. So plus, I think, let me verify that. I'm having trouble remembering. No, it is just the area, or just the distance. So times, let's see, the distance to the centroid of this one. Now that was the 0.674. Let's see, but We need to measure it from down here. So let's see, that would be what? I'm going off the video here, unfortunately. We'll move that down. 3.35 inches squared multiplied by, so I need that centroid from the bottom. And I'm having trouble thinking here. Oh, here we go. 12 plus 0.387 less 0.674 inches. Okay, so that should give us the area here multiplied by its centroid from here, and the area here multiplied by its centroid. Yeah, there we go. Okay, all of that has to be divided then by the total area. So 14.6 square inches plus 7.35 square inches. Okay, so this should give us the centroid location. Let's see if the units work out right. We'd have, yeah, we'll just have inches. And so when we plug that into your calculator, actually we should get the exact same thing we did on the spreadsheet. So I don't know if there's a lot of value in plugging that in. But there's the location of the centroid. So according to Excel, this comes out to 7.913 inches or so. So there's our centroid, which makes sense because the area distribution of the I-beam is much larger than that of the C-channel. So that centroid makes a lot of sense. But the C-channel has a lot of area. So then the next thing to do is to calculate the area moment of inertia about that centroid, about that 7.913 inches. To do that, we just use the parallel axis theorem. You use the area moment of inertia about the original centroid of the area plus the area times the distance squared from this axis to the axis of interest. So for example, let me draw, yeah, there's some space. Let me draw the I-beam down here. Need a little bit larger version. Okay, so what we've got right now is the area moment of inertia about the centroid of the I-beam. But the centroid of the combined shape is up here somewhere. In fact, let me switch colors. I want you to understand what the spreadsheet's doing and not just use it blindly. So the moment of inertia of this area about this axis, what you need is the distance between these two. That's what this D is. Okay? So for our calculation here, just for the I-beam itself, I guess I'll put a subscript I for I-beam there, we'll have IXX, which is 303 inches to the fourth, plus the area, which is 14.6 square inches, okay, multiplied by D squared. Well, D squared is going to be 6 inches, or well, 7.913 less 6 inches. Does that make sense? So this distance here is what, 1.913 inches, right? So the D squared is 1.913 inches quantity squared. Okay, so plug that into your calculators, please, and let's see what we get for our translated axis. Because the way the area is distributed about this axis is different than the way the area is distributed about the original centroidal axis. Okay? Plug that in if you would and let me know what you get. In the meantime, I'm going to draw the C channel up here. And go through the same kind of idea. Anyone have a number?
356.4.
356.4. Thank you. And it's not really a surprise that this is not a lot larger than just IXX because the axis hasn't been moved very far. So that makes sense. If you move the axis 6 inches, you can see how this term is going to start to get really big really quick, right? Because this is going to become 36 times 14.6. So the moment of inertia about this axis is very different from the moment of inertia about this axis. Okay? Anyway, So now let's continue with the C channel. This is going to be a little tougher because we'll need the overall height referenced from the bottom of the I-beam. Okay, so here's our y-axis. So that overall height is 387 inches. Okay, that's from here to here. And then we'll have to subtract off to get to here. We'll have to subtract off this thickness going down to the centroid, which is 0.674. Okay, so that's the height from here to here, but we want this distance, so we have to further subtract off the centroid distance, which is 7.913 from the bottom. Okay, this is the dimension we're interested in, so please plug that into your calculators, and let's see what that dimension is. Get rid of this.
This IY.
Well, it's 12.387 minus 0.674 minus 7.913. That anymore.
3.8.
3.8? Anyone second that? Okay, so 3.8 inches. All right, that's what will go in. So for the C channel, we'll have IYY plus the area multiplied by D squared. Now this D is going to be this one. IYY is 4.45 inches to the fourth. Okay, plus the area is 7.35 inches squared. Make these look like 4s and 5s. Okay, and then the distance D is 3.8 inches quantity squared. So now calculate the area moment of inertia of the C channel about this new centroid. What do we get? 13.58.
110.5.
110.58, thanks. Anyone second that? Okay. Why is this one, why was there so much change? We went from 4.45 to 110, whereas there was not a large change here. What's the difference? Why the difference? Because the centroid axis didn't move very far on this one, whereas the centroid axis moved very far on this one. Okay. Notice the parallel axis theorem, it's very sensitive to this term, right? The farther this distance is, it's to the square of that, right? So it's going to make a much larger difference in the area moment of inertia. So now the total should just be IC plus II. So just add these two numbers together, and that should be what we've got in our spreadsheet. Does it match? 466.9? I've got 467 in the spreadsheet. Well, we're close. Why the difference, though? Oh, I rounded this off. So it's only good to 3 decimal places, so yeah. Questions, comments? Okay. Let's see, we still have 7 minutes left. Let's see if there are any others we can work. My reason for going through that is I wanted you guys to see how to use this, or what the spreadsheet's doing, not just how to use it. There is another example. It's on page 347. I think we can crank this one out as well. I'm going to stop the video, though, at this point because I don't intend to work this one on the board.